everyone, and welcome back to How Did You Solve? In today's video, we're going to be looking at one-dimensional motion and be solving a problem from an AP Physics C worksheet. Let's get started. So let's just have a brief table of contents before we actually get into the problem. We'll first introduce the problem and understand each exercise that they ask for, and then we'll get into the graph interpretation as the problem does include a graph. So we'll be understanding and analyzing the graph. And then next up is actually solving each question step by step. And in conclusion, we're going to do a quick overview and then reflect on it. So let's start with the introduction. First, let's look at a brief outlook of what one-dimensional motion is. So one-dimensional motion describes objects moving in straight lines. If an object's velocity changes with time, the object is said to be accelerating. When restricted to one dimension, there are only two possible directions for the velocity and acceleration vectors to point in. So this could either be positive or negative directions, or it could also be whether it's vertical or horizontal. But it can only follow one component in one direction. You cannot have both vertical and horizontal motion. That would be two-dimensional motion, which is often looked at in projectile motion. How is this problem helpful to you as a student in AP Physics? It includes a lot of graph analysis, so since this problem has a graph, we must analyze and form calculations from it. It also helps us visualize the motion involved with the object. There are also various differences in motion in this problem. It allows us to notice the vast differences between all components of motion, which are position, displacement, distance, velocity, and acceleration. So, what is the problem actually? The problem is that you're not subscribed to our channel. I'm joking, but you should definitely leave a subscribe as well as follow us on our Instagram on How Did You Solve. Now to the actual problem. An object moves along a straight line and the velocity as a function of time is presented by the graph, which is on the right side of the screen. So we have velocity here, and then time here. And then more into the problem, it has four different parts. So part A, find the acceleration of the object for the time intervals. So we have from 0 to 5 seconds, 5 to 10 seconds, 10 to 15, so on and so forth, until 25 to 30 segments. So basically, it is split into segments of 5 seconds each. Part B, find the traveled distance of the object for the entire trip. Now we have a keyword here that we'll be looking at later, distance. In part C, the same thing, except we're trying to find the displacement, also a keyword. Finally, they want us to graph the position and acceleration of the object between t equals 0 and t equals 30 seconds. So basically, the position and acceleration of the object throughout the whole time. Now we're going to be looking at the graph and actually trying to understand it quickly. So basically, as we said, we have an object moving for 30 seconds, exactly 30 seconds, and as it's one-dimensional, it's only either going to be horizontally or vertically away from the origin. So that doesn't really matter. All that matters in here is that the velocity goes in the positive direction and then goes into the negative direction. So in physics, when you see positive or negative, it doesn't have to necessarily mean it's decreasing or increasing. Of course it is, but it could also define the direction of the object, whether it's moving away from the points of start, the initial point, further away, closer, or in the west, in the east, north, or south. Of course, so since we have velocity and time here, we could find the acceleration easily. We could also find the position, and then define other components, so on and so forth, which we're looking at later. Now let's get into the third part, which is solving and answering each question step by step. So part A, find the acceleration of the object for the time intervals, 0 to 5, 5 to 10, etc. seconds. Now how do we actually find acceleration for a velocity time graph? Essentially, all you're doing is finding the slope of each interval. So that would mean dividing the change in velocity by the change in time based on the given interval. So we have here, as you can see, A should have an arrow though because it's a vector, is equal to change of velocity over change of time. So we would just be finding the slope here, 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 and here. So let's get into solving this problem. To find the acceleration, as I said, we would be taking the slope of each interval. So for t for t is equal to from 0 to 5 seconds, we would have a is equal to the change of velocity over the change of time. And this gives us, we have to take velocity final minus velocity initial. So we have 4 minus 0 over 5 minus 0, the time. Which just gives us 4 over 5 meters per second squared. Do not forget your units, as acceleration will always be meters per second squared, unless defined otherwise. And then for this part, t is equal to 5 to 10 seconds. Once more, we have a is equal to change of velocity over change of time. And in here, we have a constant velocity. So essentially, when you know that when you have a constant velocity, when it's not changing, it means that the acceleration is 0, because there is no change in velocity. So this just means 4 minus 4 over 10 minus 5. You get 0 over 5, and that just is 0 meters per second squared. Moving on to the next segment, for 10 to 15. 10 is equal to 10 to 15 seconds. Equal to. Once more we have 4 minus, or rather in this case 0 minus 4, because the final velocity is 0, over 15 minus 10. And this gives us negative 4 over 5 meters per second. So this could mean that it's decelerating at a constant rate, but it could also mean that it is changing direction. So it could be going this way, and then it suddenly took a turn. Now you just do the same exact thing for each of the other segments, which we can just look at the answers in the next slide. So as we saw, we did the first 3 intervals, and then the last 3 intervals are practically the same, where you have the graph to be going in the negative velocity, so negative acceleration, goes again at a constant velocity, so you have no acceleration, and then it has a positive change of velocity, and so you have a positive acceleration of, and as you can see, all of them are 4 over 5 when disregarding direction. Now we are going to go to part B, which is find the travel distance of the object for the entire trip. So let's make sure to know what exactly distance is and how to differentiate it between displacement. So to find the distance, first of all, traveled from a velocity time graph, you just want to find the area under each segment. In our case, our graph is very simple, as it just has linear lines, if you want to call it that way. If it were to be curvy lines, then you would have to use some kind of calculus, and in that case it would be using integrals. So when finding the distance, even if we find the area, we have to disregard the direction, whether it's positive or negative. This is because distance is a scalar, so only magnitude matters. Now let's do it again. So in this little segment here, we have a right triangle. This segment here, we have a rectangle, and then this one, a right triangle. And since we realize that this is the exact same change as this, then it will just be negative. But since we're looking for distance, the negative doesn't matter, so they will have the same values. You could either use the areas for right triangles and add them up with the rectangle, or you could use the trapezoid formula. I will go through both. So first let's begin with this segment, the right triangle. As we know, the area of a right triangle is 1/2 base times height. So in here, the base is 5, 1/2 times 5, and the height is 4. And 5 times 4 is 20, times 1/2 is 10. And since we're looking at distance, it's going to be in meters. And this makes sense because it cancels out, since the base is in seconds, and then this is in meters per second. The seconds cancel out, and you're left with meters. Now, the area for the rectangle, I'm going to name this A1, A2. is just length times width, or base times height, if you will, where we just have once more 5 times 4. 5 times 4 is equal to 20 meters. And finally, another right triangle of the exact same dimensions, and we're just going to get 10 meters again. A3 is equal to 1/2 base times height, 1/2 times 5, and 4 is equal to 10 meters. Alright, now going into the trapezoid method, if you know your formulas, you will know that a trapezoid formula is, the area of it is big B, so the larger base, plus the smaller base, over 2 plus times the height. That will equal the area. So you just replace the bigger base with the interval of 0 to 15 seconds, so it's just 15, plus the smaller interval, which is just 5, smaller base, divide that by 2, multiply by the height, and that is 4. 4 over 2 is 2, 15 plus 5 is 20, and then 20 times 2 is equal to 40, as we will later find with the regular method. So this is very much a time saver, but if you don't have your geometrical formulas memorized, just stick to finding the areas of each different segment. Now adding all of this up will give you the distance for this segment. You do the exact same thing for this segment, but since we know they're the same, we don't really have to repeat the procedure. So all we would do is all of this times 2. And this is going to give you 2 times 10 plus 20 plus 10 is equal to 40, and you get 80 meters. There we go. So the travel distance for the entire trip is 80 meters, and this is because we disregarded the negative. Part C. Find the travel displacement of the object for the entire trip. So now, how do we find displacements from a velocity time graph? We do the same exact thing, where we find the area under each segment. However, we consider that direction, whether it's positive or negative. And this is because displacement is a vector, so magnitude and direction are considered. In this case, we're just going to look back again at our graph here. And we know now that since this will be negative, instead of just being 40 meters, it's going to be negative 40 meters. So in here you have 40 meters and negative 40 meters. Now you sum up everything, you'll have 40 plus minus 40, and that just gives you 40 minus 40, which is 0 meters. And this makes sense. This actually tells us that the object has returned to its initial position. It went somewhere, and then it came back all the way to the same position without any other obstacles, if you were to call it. Okay, moving on to part D, where they ask us to graph the position and acceleration of the object between t equals 0 and t equals 30 seconds. So, graphing the acceleration would be fairly easy, as we already defined what the acceleration is for each time segment. So all we would have to do is plot the points, and we'll look further into that and what to consider when graphing acceleration, that is constant. But for position, we're going to have to do a little bit more for it. So as I said, for position, we just find the area under each segment if we haven't already, making sure to consider the direction, because we want to know whether it's going further away from the starting point, getting closer, or going away on the opposite direction. So whether it's positive or negative. And then when we're plotting it on the graph, we want to plot the cumulative points, which means adding them up to each other one by one, like one before the other, on a new graph. And then connect them with curves, and curves especially because since the velocity is changing, it could be reaching a point faster than it did to the other, so you aren't exactly sure whether it moved linearly. As for acceleration, excuse me, with what we found earlier for the acceleration by dividing the change of velocity over the change of time, we just simply plot the points on a new graph and connect only the segments with lines. So it wouldn't be continuous, but rather they would be jumping lines, which may seem a little unrealistic. In fact, completely unrealistic, because in real life, a car, for example, cannot just jump to a certain acceleration. It has to accelerate gradually or decelerate gradually. But in this case, we neglect and disregard the realistic circumstances and just focus on simple physics. So now let's actually work it out. Okay, so we will be using the graph from before, where we sectioned out each part where we found the areas. We know that in here, it's equals to 10, let me just erase this. So 10 meters here, and here we have 20 meters, and here we have 10 meters again. Why it's positive is because the velocity is still in the positive even though it's decreasing, and it means it's still going in that same direction, the positive direction. And then it only changes direction here, so it would go lower. I mean, further away in the opposite direction. Now in here, all of the displacements are negative, considering they're going into the opposite direction. So still the same values, but just in the negative. And then this makes sense, because the total displacement would be 0, since it came back to its original point, and the total distance is 80 meters, if we disregard the negatives. Now let's plot this out in our new graph. So first let's list out what we had. We have 10, 20, 10 again, and then negative 10, negative 20, and negative 10. Okay, let's start. So let's start out first by making a scale for our graph. I'll be doing that real quick and coming back to plot out the points with you guys. So it's important to have your scale neatly figured out when making graphs. You don't want to mess it up just by mistakenly not sectioning them properly. So make sure you count your grid, or use a ruler if you're doing it on paper, which you'll be doing anyway on an AP Physics exam or in class. So I've sectioned it here by 2 cubes for 10 each, and here 3 cubes for 5 each. Although it wouldn't really matter considering we're not looking at the in-between, but it's just nice to have it neat. So let's start. As we said earlier, they're going to be cumulative, so we want to add in the other points to the last one. So first we're going to begin by 10. From 0 to 5, we have 10. Plot the point here. From 5 to 10, we added an extra 20 meters away. So that would go all the way up to 30. Right here. And then from 10 to 15, we add another 10, and that will lead us up to 40. Which makes sense, because as we said here, the total distance traveled was 40 meters. And then going back to the starting point, we're going to subtract 10 from here, which leads us back to 30. Subtract 20 leads us back to 10. And finally, we go back to the initial position. And so this is what the points we plotted should look like. They would look a bit like a parabola in a sense. It starts out in 0, goes to 10, all the way to 30, maxes out at 40, goes back down to 30, all the way down to 20, and back to its starting location at 0. So this is what your position and time graph should look like. Now let's move on to graphing the acceleration. So from what we found before, we have the basic values of 4/5, so you don't necessarily have to scale it in terms of the acceleration, but just have your time neatly placed out evenly, the same way as we did before with 3 cubes for each on my grid. And then for this one, since again you just have one value, it could be anywhere. So I'm just going to have the max value, which is 4/5 right over here. And then negative 4/5, a similar distance away at negative 4/5. Now that doesn't look very similar. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, I'm just gonna move that here. There you go. And then over here, we're just gonna spread it out by 3. There. So now let's start actually graphing, knowing that, let me just put these on here to remove it afterwards. You have 4 over 5, 0, negative 4 over 5, negative 4 over 5 again, 0, and then 4 over 5 one last time. Let's just get rid of that. Okay, so the first segment from 0 to 5, considering it's a constant acceleration, we're going to plot it out like this, a line. Basically, just a line. And then, with the unrealistic physics we're doing right now, we're going to jump all the way down to 0, and this is where you should draw your line. Once again, jumps all the way down to negative 4 over 5 for the next 5 seconds. It keeps on going at negative 4 over 5. And then it jumps back again to 0 and goes all the way up and accelerates to 4 over 5. So this is what your graph should essentially look like. Okay, so now let's just get to the conclusion, which would be a quick overview of what we went over and a reflection. So what do we know about these three things? For acceleration, we learned that it's a is equal to the change of velocity over the change of time. So if you are given a velocity time graph that is linear, you would just find the slope of each time segment that is asked from you. We also noticed that the acceleration is 0 when the velocity is constant. That is because there is no change of velocity. If you were to subtract the final velocity minus the initial velocity, you will get 0. So 0 out of over anything is just 0. And then when you are graphing acceleration, you graph it as jumping lines because it's constant for our case. It may not always be constant. It could be linear or even a curve, but in our case, it's constant. So they would be graphed as jumping lines. For displacement, we have to consider the direction, whether it's positive or negative, because it's a vector. So it's not just magnitude, it's direction as well. And if the total displacement is 0, it means that the object that was in motion just went back to its original position, its initial point of start. And as for distance, we only consider the magnitude because it's a scalar. So in that case, direction, whether it's positive or negative value, does not matter. And the distance will also always be greater than displacement. That is because you're summing everything up, no matter whether you went back to some place or not. For position, we know that it's the object's location from the origin, which is the initial position. So how far it strays off from the initial position. It could be at 0, it could be at 5. That depends on the problem and the situation given to you. But it's just how far or how near or how far away from the opposite direction it is. We also must consider direction. As I said, it could either be going the opposite way. And when graphed, you graph it as cumulative points. That way when you reach the final, like as we saw when the velocity reached 0 in the first part of the motion, it was at its maximum distance away from, maximum position away from the original point. And you also connect it by curves. And there's more on graphing here. So as we said, acceleration is jumping lines. If it's constant and it's obtained from the change of velocity over the change of time, in this case we have a slope. Otherwise it's going to be a derivative if it's not linear. But for us it was very simple, just the slope, basic geometry. For velocity, it's connected lines of changing as given in the graph. So we did have a changing velocity, it was going at a linear rates. But sometimes it was just a straight line, which means it's a constant velocity, there is no change in there. And for position, it's curved lines obtained from the area under the velocity and time graph. So now for a brief reflection. Now, there are problems like these which are very simple and straightforward to understand and solve. they shouldn't take you that much time. This is just a thorough presentation on how to solve it step by step. But once you do various kinds of practices regarding this type of problem, you'll be doing them in under 2 minutes, honestly. The longest that could take you is probably the graphing and the calculations if the lines are not as linear or not as straightforward as our graph. But really, it's the most basic components of mechanics. It's one-dimensional motion is what you learn at the very beginning. In general, don't let AP Physics C or really any other course, AP Physics 1, 2, and then C, this one is mechanics, and then there's electricity and magnetism. Don't let them intimidate you or frighten you. Essentially, you are signing up for an advanced placement course and or even the exam, and so it will be difficult, of course. It's a way to challenge yourself, but it also really helps you if you're going to pursue something in that field at university. So you can, even if you pass with a grade higher than a 4, like a 4 to a 5, you can earn those credits and completely skip the introduction course in university. So it can be very beneficial. So really don't let it take you down. If you're stuck in any way, make sure you look up various kinds of lessons. There are plenty of resources on the internet. You've got a bunch of free textbooks you can look at, PDF files, videos on YouTube from generous YouTubers. You got us, How Did You Solve? We are here to help you. You can shoot us a DM on Instagram and we'll reply as soon as we can. We'll guide you through the problem and then try to help you out. You can even leave suggestions in the comments, either on our posts on How Did You Solve or on these videos that we launch on YouTube, asking us what you want to learn more about, and we'll gladly try and do that with you. Help you figure it out and solve it. You can even send us specific problems. We'll do our best to solve it with you. And so, as I said, don't let AP Physics try and take you down. In a way, you want to take it down. You want to show him you're stronger. And that goes for any AP course or exam or like any higher advanced level course. It is designed to make you feel challenged. It is designed to make you feel puzzled and lost. But with the resources we have at hand, we should be really able to continue and strive and do our best. Put in a good amount of time, manage your time in studying it, and if technically you go through all of that, you will do well on the AP exam. And I guess that's really it. We learned a lot from this problem. We learned about graphing and the different kinds of motion and how we can get them. And that is the end. If you enjoyed this video, please leave a like, share it with any of your fellow classmates or friends or even anyone outside that needs this kind of help. If they don't understand what this is, leave us comments of suggestions or if you like this video. Follow us on Instagram. I know I'm saying this a lot, but it would be really appreciated if you do. And yeah, that's all there is to it. Have a nice day. Bye.